Maximum parsimony. The parsimony principle states that the simplest hypothesis concerning an observed phenomenon must always be preferred. Parsimony methods search for a tree that minimizes the number of character state changes, or evolutionary steps. This tree, called maximum parsimony tree, refers to the simplest explanation of the evolutionary history for the species in a given dataset, Felsenstein, 2004. Let be a dataset containing species. Each species has its, where digits the character state of species I at site j. Given tree with node set vt and branch set et, the parsimony score of t is defined as, Swafford et al., 1996. World refers to the weight of site j, Vjandujar, respectively, the character states of nodes van Watt sites for each branch, u, v, entonces the cost matrix, such that cvj, ui, is the cost of changing from state to state to e. The leaves of tear labeled by character states of species from d, i.e., a leaf representing kth species has a character state for position j. The following properties can be noted from equation 1. Parsimony criterion assumes independence of sites, i.e., each site is evaluated separately. The calculation of the parsimony score only takes into account the tree topology. Thus, the parsimony criterion does not incorporate other information, like branch length. There are several variants of the parsimony criterion. One of the simplest is the Fitch Parsimony, Fitch, 1972, which assumes a unitary cost matrix such that xi equals 1 if x does not equal y, otherwise xi equals 0. The Fitch and even other more complex variants of parsimony can be even generalized for arbitrary cost matrix and restrictions of state changes, Sankoff, 1985. Given a tree T, it is necessary to determine the character states of its internal nodes such that PST is minimized. This is also known as the small parsimony problem. In the case of the Fitch parsimony, a post-order traversal int is enough to minimize PST. This procedure is known as Fitch algorithm, Fitch, 1972. In the case of generalized parsimony, the small parsimony problem can be solved by applying the Sankoff algorithm, Sankoff, 1985. Having defined an algorithm to minimize PST for a given tree T, we should determine the tree T such that PST is the minimum for all tree search space. The problem of finding T is called large parsimony problem, which was proved to be NP-hard, Felsenstein, 2004. However, several heuristic techniques have been proposed to overcome such a difficulty, Golubov, 1996.